Okay, so today we'll start looking at the other graphs for the other trig functions here. So we're going to define a function x tangent of x. Yeah, so it's just very similar to sine and cosine. Tangent, we can also see that as a function. So now, having created a function on its own over here, we can get the graph of that. Right? So let's sketch down. Let's work through a few values right here. So you guys go ahead. Once again, have your unit circle ready. So we want to construct a few inputs. Table values for a few inputs here. So x here is playing the role of an angle, right? And so we can think about x equals 0, the angle is 0. You can go with the angle 5 or 6, right? 5 or 4. 5 or 3. And 5 or 2. Okay. So quickly put in your calculation those outputs values again. These values are in exact format. So anyone would like to get me the first value for angle 0? Tangent of 0 is 0. Remember, tangent is the value for sine over cosine, right? Anyone on pi over 6? 3, 3. Right? Which is somewhere less than 1, right? And then what about the pi over 4 over here? 1. Okay. What about pi over 3? 3. Right? It's higher than 1. So it's all going up, right? The values are all going up. And then what about pi over 2? Anyone?
Undefined.
It is undefined. Because the cosine in the denominator is a 0. Yes, undefined. So I'm going to extend the table a little further here. So after pi over 2 under the unit circle, we're going to swing over to 2 pi over 3 here. Right 2 well, 2 pi over 3. And so tangent of x. And the next one here was a pi over 4. Okay, so, and then I have to go complete the whole circle again. All right, anyone would like to give me 2 pi over 3? Negative root 3. And then the pi over 2 pi over 4 here. Negative 1. All right. Now that should be enough. Forget it. And now I'm going to put it on the actual graph. So there's no need to make you guys complete the whole table because then you kind of get a hang of it. So now let me turn that over to the graphing viewer here. You guys see that right here, right on our graph. That right now it's blank. Here's the x-axis, right? And these are the y-axis. I can't even make my graphing utility here to show the pi over 3 and the pi over 6 here, but I'm going to go with the basic pi over 4 and so on and so on. Right? So let's have a look at the picture over here. I'm going to, so from 0, we started here, right? We started right there and observe the table of values. Remember, when we're graphing the y value, the output value for tangent is the vertical, right? So as I change, so now the graph goes like this. You see how it's rising like that? See, at pi over 4, right here, when I put the mouse cursor right there, at pi over 4, we got a 1 that's consistent with our table value. You guys follow that? Okay. And then the pi over 3 is right about, pi over 6 is right about here on my mouse cursor, and it's right at about root 3 over 3 when we're doing the real calculation. So I mean, that's why the graph was rising like that, but it's rising. Now, you see at pi over 2, according to our table of values, we got an undefined. That means here we have a vertical asymptote, right? The graph is getting close to it. So now I'm going to zoom it out. Right? And the graph, I didn't complete too far yet, but the graph keep getting closer asymptotically. Keep getting closer to that vertical line at y, at pi over 2, but it's not going to cross. And now when we go far enough, it's going to swing to the other side. See how there's a bottom part that starts rising up right there? Right? There's a bottom part that starts rising up right there. And it hits to, okay, so now let me move it back in right here. Okay. Right, so there's a vertical asymptote here. Now I'm going to keep keeping that, and so it hits right to pi right there. Okay. And then, so at 3 pi over 4 that you guys seeing right here where my mouse cursor is at, right? It was a -3 and -1, just like that, right? Consistent with the table value. So the values first, from the left to the right, the value was rising infinitely high, right? Rising infinitely high right there. And then it didn't cross through that line. There's a vertical asymptote right at pi/2 right there, right? And the graph just jumped right around that. And then so it jumped to the bottom side right here and then start and continue to head up right there, right? And then it heads right to, so when we were at pi/3 pi/4, we've got it at a -1 halfway between the, so right at 3 pi/4 we got a -1, and then at that 2 pi/3, which is somewhere around here, right? We were down at the -√3 right there. Okay, and so now I didn't put this value pi on the table of values earlier, but you guys can quickly confirm with that. What's tangent of pi? It's 0, right? That's why it hits right back to pi right there, right? So now I'm not gonna need you to, we don't need you to complete the whole unit circle, but now let's observe. So the whole unit circle, the x values go from 0 to 2 pi, right? Equivalently right there on the unit circle. 0, right? Okay, to 2 pi. So right now we're already halfway through the unit circle, right? So let's go ahead and complete the unit circle rapidly right here. So when we're on the, so now look, there's a vertical asymptote right here. So now I'm going to continue to complete the unit circle. So we're going to keep going further. So you see how the graph rises again, right? Just like the beginning piece right here, right? Just very similar to that beginning piece. Let's keep rising and then asymptotic again at 3 pi/2. And then it has another rising portion at the below right there, and it stopped at 2 pi. So as it turns out for us right here, now we put the vertical asymptotes in. If we go the complete cycle of 2 pi right there on our unit circle, the graph here for tangent has 2 vertical asymptotes. See what I'm saying now? Right, we got one right here at that 3 pi/2 as well. Right? You guys can double confirm right here. Why don't you do a quick calculation for me? What's tangent of 3 pi/2? Yeah, it's another undefined. That's the reason why we have vertical asymptote right there. See what I'm saying now? Right. So now let's have a look at the structure of our graph function. Of our tangent right here. Now, the truth here is now we draw the graph here. We drew the graph here for the one complete rotation of the unit circle, right? But as a matter of fact, you can see that it's already finished. This graph right here already is a repeat of that portion right here. See what I mean? I try to drag it back to this particular portion right here. From 0 to pi. See what I'm saying that? And then when we go to one complete cycle on the unit circle right there, then it's the same unit right here being repeated. So you can see that we repeat one more from pi to 2 pi, right? So one unit circle from 0 to 2 pi, right? We complete actually 2 cycles of our 2 basic units of our tangent graph. You ready? Okay. So now when we're looking at the actual anatomy of the graph now, so the tangent, the way how I see that now, one basic unit. Just like the sine and the cosine, the tangent graph is just a matter of a basic unit being repeated. So one basic unit actually only starts from 0 to a pi. You guys follow? And then halfway at pi/2 here in this particular picture, right? Y equals tangent of x, just that ordinary one. And right at halfway in your units, we have a vertical asymptote, and the graph goes like this. Goes up. Bottom up, come to that point 0. See how easy that is to draw that right there? Okay. Again, you can just close your eyes and do this. Horizontally, right? Starts, and right there. Halfway, you got a vertical asymptote, right? And then it starts at the beginning point, rising up asymptotically, right? And then at the other part here, rises and hits that end point. See what I mean? Okay. And then so you got to start for your basic units right here. It starts, and right, just like that. The line here, which is currently right now, this line is our x axis, but the x-axis currently for this function here is pointing in place of the center line. So there's also a center line, right, for this graph. You ready? So any graph of, so generally speaking, right, any tangent graph got the center line, right? It's got starting points, right? It's got a start, it's got an end, right? So the total distance from start to end right here, that's our period, because we're repeating that basic units, right, infinitely many times. Right, you doing that? Right. And so, and then there's this line right here near the center, the center line. That's the common structure of our graph then. And just like that, I've been listing down center line, right? So for this function, tangent of x, y equals tangent of x, right? The center line is at what? The x-axis, which is y equals 0, right? I'm going to come back and talk about the amplitude a little later. But then we got a period. How big is this period for this specific function? Once you're seeing that through the picture? Yes, for this graph, it's 5. Yes. This is the ordinary. So unlike sine and cosine, this function here, take the period only of pi. 5 units. And then for this ordinary tangent, we got starts at x equals 0, right? Specifically, and we got the end point at x equals pi. And this is simply because the ending, again, ending equals the starts, right? Plus period at our tangent of x, right? The ordinary tangent of x. Let's look over to cotangent. Now you can see that even tangent has some similarity with the sine and cosine in terms of the center line, the period, start and end right here. And I didn't even talk about the amplitude, and then we'll come back to that. Right. But now I'm just going to show you the graph of cotangent, and then you don't need to worry about the points. For the graph of cotangent, right. Now let's go ahead and observe on the screen right here. The beginning of the circle, right? It's right here. So when the angle is 0, right? And ending at 2 pi, which is right here at that end. When I put my mouse further at. You guys follow it? So let's see the behavior over here. So I'm going to increase this slider over here. So here's how it works. You see how the blue graph behavior is acting like that? Okay. So it seems like it starts from wherever height it is way outside of this viewing window, right? And it keeps dropping, and hits the center line, hits the x-axis, right, at pi over 2. Right? And then it's bent, its structure, and then keep falling down like that. So it looks like it has asymptotic behavior. This graph here has asymptotic behavior right at that y-axis, right? And then it's also having the asymptotic behavior right at that line, the pi right here. See what I mean? Now let me zoom it out a little further. Okay? And then now clearly it's making it clear that it's got asymptotic behavior. And see, by the way, there's already some piece of the other side of that asymptote here showing out. And so as we continue with that, right, that's actually already a replicate of that first basic unit. So I'm going to continue to complete one entire unit circle. So the unit circle starts at 0, right here at my mouse cursor. Right? Start at 0, and if we're adding at 2 pi, which is right over here, right, then actually it looks like we repeat this wave over here twice already. Saying we have it twice in that wave again. Okay, and so really, in that way, one basic unit you can see. Let me roll back to that point right here. One basic unit you can see is simply just this portion right here from 0 to pi. That's one basic unit of our cotangent. It has a crossing point. So in this case right here again, the center line of our graph is right at the x-axis. So we got a center line generally, right? And then we got two vertical asymptotes. Now let me put in the vertical asymptote. See those dotted lines I put it in right there? See the graph is asymptotic to those like that. And the shape is falling down like a waterfall, right? The shape is falling down like that. Right? And as I zoom it out, see, no matter how far I zoom out like that, it's just restricted in between those two. And then as I increase that, right, we got another duplicate of that. So guess what? There's another vertical asymptote and it's 2 pi again. See what I mean? So why don't you look on the picture right there and let's try to do some math to make consistent. Why do we have a vertical asymptote at 0? At x equals 0. What do you think? No. Yes, we define our function y equals, right, cotangent of x. See what I mean? And then the graph behavior shows a vertical asymptote at 0, at pi, and at 2 pi. So think about the inputs table here. Table values 0, pi, and 2 pi. What do you think the outputs for these values here when y equals cotangent of x? Cotangent of 0? Anyone? It's an undefined. Simply because this is what? This is cosine of 0 over sine of 0. Remember the way how we define cotangent like that? And cosine of, sine of 0, the denominator here is 0 value. That's why it's 0. Are we good? Right? And then before you guys copying things down here, I want you guys to think about the next two here. Okay? We will calculate cotangent of pi. What do you see? It's another undefined. That's why we have another horizontal and vertical asymptote here. It's cosine of pi, right, divided by sine of pi, which is another 0 in the denominator. Sounds good. And what about the 2 pi here? That's why it's consistent with our graph here having 3 vertical asymptotes. Those vertical asymptotes, right, at these places here. Sounds good. So now we're looking back at the actual structure I showed earlier on the screen, right? The real structure as far as the basic units. Because remember, these functions here, these trig functions, we started that idea since the days when we're looking at sine and cosine, right? Now we're we're transitioning into tangent and cotangent with. It's all built from one basic unit. The entire graph is built on one basic unit. So the basic units for cotangent, here's how the way how I see it. Well, for this graph specifically, then it started, see, right at x equals 0, we got a vertical asymptote, right? And then right at pi, right, we got another vertical asymptote. And then halfway is some point here, so the graph was behaving like this. It's falling, right, and falling like that, and cross through, right at that halfway, cross through the center line. Currently, in this graph right here, the x-axis. And then continue crossing through, and then continue being asymptotic. See the basic structure of that, okay? And that's why when you completed the unit circle, right? Pi is here, the complete unit circle is at 2 pi, right? That's why we have another vertical asymptote. And then the graph went like this again, halfway between that next period, right? Halfway between that next period, the graph repeats itself, just like that. So guess what? If you want to complete the whole graph right here, then it's just going to be like that. Or from 2 pi, you got another one at 3 pi, right? That's another vertical asymptote. Asymptote like that, halfway between that, right, it goes like this. See how easy that is to get these rapid cotangent. So all of that in the end, I only need, right? So I drew that, but really I'm going to easily erase it out. I know the basic structure of that. So everything is built on this one basic unit. Now you guys go ahead and answer a few of these information. For this particular function, the ordinary cotangent, where's the center line? Yes, y equals 0. The x-axis. Good. And I still didn't talk about the amplitude, including the tangent amplitude, right? But the periods here, what do you recognize? The total windows that your basic units take, right? How far is that? How far is that total window? I mean, how far total distance is that? Pi. So the ordinary cotangent, right? Got the total window being pi. And then it starts here. It starts at the asymptote. It starts at the asymptote, but in the end, it starts at equals 0, right? Meaning we place the plus asymptote at. It has to start at the asymptote here. T, and then it's standing at the other asymptote, pi. Right? Another, right? Another asymptote. And then the rule for getting that always again is the start, right? same structure. So the concept of the amplitude, right? The whole idea about amplitude is that when your graph is waving up and down, right, and has a high peak for the wave, and then it measures how far the wave swings away from the center line. Right? That's why there was the concept of the amplitude back in the graph of sine and the graph of cosine, the sinusoidal graphs here. But now think about our two graphs here. The graph of tangent. See, starts and halfway, you got a vertical asymptote, right? Swinging up, doesn't stop, right? And then all of a sudden just magically break to the other side here, like this. Do you think we even have to worry about amplitude at all? No, right? We don't have to worry about amplitude, so we're just going to indicate it non-applicable here. And then it's the same with the cotangent. The cotangent here, right? So then you can also go back to that. Now right now I'm putting in the information for cotangent, right? But you can also go back to that same list for the tangent right there. And right at that line about the amplitude, we have the non-applicable. Okay, right? So the same way right here for our basic units of the cotangent here, see? Yes, you got a period, some starts, right? Some end, starting and ending, or on the vertical asymptote, and our graph goes like this. But the truth now is that it doesn't matter. I mean, it's just going to keep expanding further up and further up without any line. I mean, without any limits, right? The sinusoidal graph stops at a certain height, stops at the bottom, certain bottom. See what I'm saying? Now that's why there's the amplitude. But now for this thing right here, just keep blowing up, right? And then keep falling down with that between the vertical asymptotes. And that's why for cotangent here, again, looking at the amplitude is something that's not applicable here. Sound good? That's still a vertical scaling, right? That's still a vertical scaling, but then we don't use that as the concept of the amplitude. So as far as the amplitude here, it's not applicable. There's no way for that. Right? It's just some repetitive graph that keep growing bigger and bigger away from the center line. Sounds good? All right. So now I want you to pay even a little closer attention to these two graphs here, the tangent and the cotangent, before we go even further. I'm just going to enhance some more details here so that later on, to make things consistent with the actual scaling, and then later on you're going to be able to draw the graph now. So again, tangent in general, right? Tangent in general, what you need here is a center line. You guys follow? Okay? You need a center line. And right now I'm not even worried about the x-axis or what. There's always a center line. There's a start, right? There's an end. See what I'm saying? No? And then halfway right there for tangent, you got a vertical asymptote, right? And the graph goes like that. See what I mean? There you go. Okay. And so now that's why for just the ordinary tangent of x here, we label that right here. We put the y-axis on right at the starting point 0, right? And then the ending point here is at pi, because you know periods and pi and all that, right? So the halfway point here numerically labeled as a pi over 2. Sounds good? But now that's that other detail I want to now point out for you guys. See, back in the sinusoidal graph here, the sine and the cosine, I've been talking about the quarter points. See what I'm saying, no? The quarter points, this is one thing to catch with the quarter point. The first quarter, of course, either way how it is right now, first quarter is at the pi over 4, right? You guys agree there? So first quarter, it hits you the high being as high as specifically 1. See what I'm saying, no? It's the way it is. Right. Tangent right here. See, the first quarter, it hits you as high as 1, right? And then the third quarter, I drew my graph here, I left my graph here a little too high. Right? So third quarter in one complete period, right? It swings to as low as -1 down here. Right? That's the explanation we can see for that. Right? It's -1 for the third quarter. So the point now is that because now I still don't call it the amplitude anyway, but at those quarter it's indicating the distance, right, from the center line to those quarter points with them. I'm talking strictly at the quarter point, right? The distance, that vertical distance, is consistent with that coefficient in front of your tangent. So it's called coefficient 1. Right? That's why it's the space being 1, right? Right at those quarter points. 1 up and 1 down. See what I mean? Right. So think about it as an impact. if you're having like the tangent of x, right? So tangent of 2x, or 2 tangent of x, for example, right? 2 tangent of x, and so you can draw again. Starts, right? And right here is 0, and the pi is here. Halfway is a pi over 2 with a vertical asymptote. You guys see what I'm saying? Huh? And then whatever your scaling, your vertical scaling, you can go like this. See what I mean? You can choose your vertical scaling, right? But now, first quarter point, pi over 4, it has to reach as high as that, okay? Because that amount, if there's 2 spaces up, agree with us. And then third quarter point again reaches 2 spaces down away from the center line. Okay? And then once you got that for consistency in your scaling, then you're going to start drawing that asymptotic major. And that's how your graph is even more scaled out vertically. See what I'm saying? No? Okay. So that's just one way to enhance your understanding. Okay. And then the same with the cotangent, right? All right, cotangent of x. Just any cotangent, Get it? There's on the center line, there's a center line, right? There's a start that we place a vertical asymptote. There's an end that we place a vertical asymptote. So for cotangent right here, for any basic units of a cotangent, right? We put a vertical asymptote at start. We put a vertical asymptote at the end. Halfway right here, right? Halfway is where the graph falls and cross through with that, right? It falls from the left high, falling down low to the right, right? And then cross through right halfway, and then cross down and go down further asymptotically to the second vertical asymptote. So halfway right here, and since our graph here is the ordinary cotangent, that's why it starts at 0 vertical asymptote. Have another vertical asymptote at pi, so the halfway point is a pi over 2. You guys follow it? Right. But then it's the same rule with the tangent. The first quarter right here, pi over 4, right? First quarter of pi over 4. That distance it hits right here. The first quarter and the third quarter, that distance it swings away from your center line. Right? That distance we call that it's a 1. Yeah. Right? That distance right down here is a -1. You know what I mean? Right. So you look right at the quarter point to measure how far your graph scaled away from the center line. Vertically scaled away from the center line. Right? So in that case, think about if you're looking at a 1/2 cotangent of x, for example, right? And the way how I see it, see, center line right here, concentric scale, this is a 1, right? This is a -1, so this is a -1/2, right? This is a positive 1/2. See what I mean? Right. And so starts and halfway, right? And it's pi, halfway is at pi over 2, right? 0, we've got to put 2 vertical asymptotes at start and at the end. But now quarter point is going to hit that high being 1/2. Third quarter point is going to hit that low being -1/2. Right? So your graph looks like this. Still the same fundamental shape, right? That's how you can keep track of the scaling consistency of that. You know what I mean? So the first quarter point here swings only as far as 1/2 away, right? And the third quarter point only swings only as far as 1/2 vertical distance away from the center line. Right. So now I'm going to show you guys an example here. Let me now erase that board. I keep focusing on the idea of the start, the end, the center line, right? And then the quarter point, the halfway point, because when you're graphing these here, let's call it now, we're talking about these new functions. So let's look at an example here. Tangent, right? Tangent. So the graph is supposed to look like this. Yes. See, center line, start, and halfway there's a vertical asymptote, right? And then it swings up, swings down like that. So around the vertical asymptote. That's everything I need to know right there, as far as the basic structure. See what I mean? But so now, in order to get the exact one for this specific function right here, you got to know where the center line is, where to place your center line, right? See what I mean? Right? So where do I place it? How do I know where to place a center line? That coefficient, that last function term, like the sine and the cosine, right? So the center line here is y equals what? -1. what I mean? Right. So now I'm putting it in for my actual graph right here, and you can start doing that on your graph. The x-axis is here, but at -1 down here. That's where I have my center line. See what I mean? So let's start it, guys. You guys will be that. The center line is at -1 as we track down. Sounds good. Okay. We don't really have to worry about the amplitude. So amplitude here we can leave that non-applicable. Okay. But then there's a way to check for scaling consistency. You already call that scale right here. That much distance is a 1, right? So above right here, that's a 1. Okay. And then I'm going to check back with that later. Now we got the period. Okay. Same rule with the trig function. That coefficient there in front of the x, right, inside of your function right there. Right. The standard period for the ordinary tangent is pi. When I call it standard period, I mean the period for the usual, just the ordinary tangent, right? It's a pi. You guys follow it? But now we want to check that. Same rule, we divide the standard period by the absolute value of that coefficient. See what I mean? Okay. So now it turns out the period for this function here is only a pi over 2 window. Sounds good? Right. And then you got to start here. How do we identify the start here? To identify the starts, very same trick that we've done. That's why we spent a good amount of time learning about the sine and the cosine function. From right here, I'm going to rewrite my function as, I can rewrite it as y equals 1/2, right? Tangent in brackets. I'm factoring out that front coefficient of the x. Okay, so -2, and then we have x minus pi over 4. You guys with me there? -1. That's how I'm seeing my function. Okay. I just factor out that coefficient in front of the x. And that's making it in parentheses x minus pi over 4, right? So this number right here is our start point. Start at pi over 4. Sounds good? And so the ending right here has to be, of course, the ending is wherever the right? X equals your starts pi over 4, but we're adding another pi over 2. See what I mean? That's going to make it 3 pi over 4 altogether. Sounds good there? So now really, I'm ready to draw that graph here. So you can call that space right here a pi over 4, whatever you want to name it. Right? Because that's our start. So right on this center line, that's our start right there. Right? But then the space right there is from that's 3 pi over 4, so another space like that. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, right? Then your ending is actually right here. It's a narrow window. 3 pi over 4 is right here. That's your ending. So that's your end. Sound good? So this time your halfway is right here at pi over 2. You gotta go asymptote right there, right? Sounds good? Okay. And then there are quarter points. Quarter, right? So on the center line, the quarter point right here. Now, it's the same way right here. When you got a negative coefficient in front of your tangent right there, it's the same as, this is the same as y equals, you can put that negative sign in front again, right? Making it -1/2. But now tangent of simply 2, you took away the negative sign. Very similar to the sine function. X minus a pi over 4. Right? -1. So now this is our final one right here. That determines the shape. So this time, see, pay attention. The center line is here. The center line is here, right? Start and halfway, you got vertical asymptote. These are the quarter. Sound good? But this time, here's how I'm seeing it. And the scale, the vertical scale here is 1, so the -2 is down here. My front coefficient is only a negative, is 1/2, right? A negative. So making the graph goes down, flip upside down right here. So start right here, but it's only go halfway. See, halfway between that, right? Halfway between -1 and -2, I swing down right here. From that start, I swing down asymptotically. You guys follow it? Right, there you go. Right, so that space right here, 1/2, and then the quarter point right here, okay, it's going to hit the 1/2, halfway between that. So it's a -1/2 there. Now any point goes like this. That's how we got the graph for that. So it's the flipped version right around the center line there, compared to the ordinary version. The flipped here due to that -1/2, right? And that -1/2 came out because we took that negative sign from the inside, bring it out. That's one property for the tangent. Right? So let's call it example 2. Okay. So again, I need to remind you the cotangent, right? The graph of cotangent. What stays in your imagination, what stays in your mind about the graph is that the starting and the ending, right? There's a center line, and on the start and at the end of your basic units, there's a vertical asymptote right at the start. There's a vertical asymptote right at the end. Okay. And then there's a halfway point, so the graph goes like this. It drops down, right? And it drops down further. See what I mean? Okay. So that's a picture of your cotangent. And then depending on how we see the later on information, we're going to identify the center line specifically right from this particular function, and we're going to identify the starting point and the periods right from here. Right? And so I also mentioned again that at those quarter points, right? And I can remind you again that at those quarter points right here, how high it swings up or how low it swings down to hit the actual graphic there, that's spacing, that amount of spacing at the quarter point. Right? That amount of spacing right there, right, that's the equivalent to the absolute value of that coefficient that stands in front. Right? So we can use that as a way to check for consistency in terms of the scaling right there. But in the end, the picture of the cotangent is what's important for us. And then there are some cases that our graph will have to be, our cotangent graph will have to be flipped upside down, right? Reflected upside down right through the center line again, due to some negative coefficient, which we can get to that later. Right? But now, so that's just two possible pictures again. So let's get to it. The center line for this graph. We've done center line frequently enough. So anyone can help me with the center line of our graph right here? Y equals 1. Right? That's part of the line y equals 1. Okay. So we've got a center line. So amplitude for tangent and cotangent, we don't really have an amplitude value, so that's not applicable. The concept of amplitude is not applicable, right, for these tangent and cotangent. The period P equals standard cotangent period. The standard cotangent period is applied, right? But then we're going to need to divide by, you see that? So to see the period clearly, you're going to need to factor out that inside of this here. So think of this function here, it's the same as y equals, right, -2 cotangent, but we factor out that -1/2 coefficient, making it -1/2. So after factoring it out, what do we have here? X plus a pi over 4 plus 1. The way to clearly see the period, we factor out a front coefficient. So that front coefficient here, absolute value of -1/2, right? That's making it too high. Factoring out the coefficient inside of factoring out that coefficient in the x term right here is also showing us the starting point right here, because we think of that as minus -pi over 4. And that's extra interpretation of that. So our starts. It also means we place the first vertical asymptote, right, at x equals -pi over 4. And then the ending vertical asymptote is at and right here is x equals -pi over 4. And we add in with the period is 2 pi right here. That's coming now be 2 pi minus pi over 4. 7 pi 4. Right? After we do the math. Yeah. So after all of that information, we should be ready now to make our good sketch of the graph here. So I gotta mention again. I gotta also further mention we already seen this from earlier lecture when we were working with the tangent here. Tangent of a negative input is the same as putting the negative sign in front of our tangent, right? And treating that as the usual tangent, just like that example I demonstrated earlier. And so cotangent actually is going to behave exactly the same. So I'm talking about when you're looking at cotangent of a negative input, you guys see the reason why I'm mentioning that? Because of that negative input right here. Okay. So when you're taking cotangent of a negative input, it's the same as we can also do the same thing, put the negative sign in front of our cotangent. That will make that negative cotangent of the usual positive input. Okay. So in our case right here, think about the consequence. If we bring, so here we're looking at cotangent of a minus 1/2, right? And that is also, you can think of that as bringing the negative sign in front, but the negative sign in front counted together with that negative sign here, making it all together a positive 2. Positive 2, cotangent of now just regular 1/2 right there, right? And then x plus pi over 4 and plus 1. So with this final version right there, how we're writing it, it's making it so clear about how we're doing the starting point and all that. I mean, starting point is still the same, right? And then period is the same, but then this right here now, positive sign coefficient is responsible for, think about the two choices. Are we going with, see, vertical asymptote, are we going with this version or the other version, the flipped over version? Which version are we going with? The normal one, right? The ordinary one. I mean, so we say this flipped version only when the final coefficient here is negative, but here we already made it positive, right? According to the calculation. Okay. And so in that case, now we're ready. Right there. You can take that scale right here being a 1, right? So we've got our center line right at y equals 1. We do that. And then our starting point is at negative pi over 4. So we pick a space right here, we call it negative pi over 4. Sounds good? So that means on our center line right here, this is the graph. And we place a vertical asymptote right, because this is cotangent, right? Right at the starting point. You guys view on that still? Okay. And then with that space here, the pi over 4, I'm going to need to go to 7 pi over 4 this way, right? So 7, so 0 is here. Positive pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, right? 5, 6, 7. So this right here is about 7 pi over 4. And the whole window here from the start to the end is a 2 pi period. You guys agree? And so right here at the ending, I'm going to put another vertical asymptote, right? So that's my start, that's my ending. Which way is halfway? That point right here is halfway, right? So put it halfway right on the center line right now. You guys see how I'm following with that so far? Right? And now we're pretty much ready. These are the quarters. That point right here is the quarter. So that is the first pi over 4, and that's the first quarter, right? This 5 pi over 4 right here. That gives me the third quarter, right? And this one right here happens at 3 pi over 4. The halfway point is right at 3 pi over 4. So I put down starting, ending, halfway point because the graph has to cross like that, right? That's the expectation. But now there's a little more precision check right here. Our coefficient in front of the cotangent is a 2, right? So in my explanation, that's very much like the explanation for tangent right there. At the first quarter, it has to take 2 spaces up to hit the graph. So the graph has to be hitting at that point right here. That's right here, right? That's 2 spaces up. Okay. So it's right at 3 together. So we got a point. You guys agree on that? Yep. Okay. And then at the third quarter, see, center line is here, so we go 2 spaces down. Okay, we got a point there. on the center line, one space down, two spaces down, about right there. The graph has to go through those points again. Okay, so now go like that, right? How bad you make that? Now it's pretty much your artistic choice again. You gotta make sure it goes through that point, and then drop right here, crossing it, right? Okay, and then okay, and now drops further down, right? And hits further down. That's your graph of the whole tangent. You see once again. From the center line, right at the first quarter, it hits two spaces up. Give me 1 second. And then from the quarter line, from the third quarter, right, it's on the center line, two spaces down again to hit the graph. That was all because of that, two times, right? That should have been even more, thank you for that part. Okay. So it should have crossed that and go more asymptotic into that line. Thank you. All right. Yes, I could have, but my board now is limited, right? But as we go further, it's going to get asymptotic to that further vertical line. So the graph for secant, graph for cosecant. Divide it into two separate spaces right here. Graph y equals secant of x, right? What is the function here? This space we are going to do graph of y equals the last one here, cosecant of x. Now let me show you the picture of the graph for secant of x here. We're going to find out y and all that. Okay. Picture right here. Okay, so just in the ordinary case again, right? Just the standard ordinary secant of x again. Let's do it like this. I'm going to drag it out, right? So you see how it's rising up again. So the point is, you can see that for the horizontal motion, as we go, as angle changing from 0 to those other angles within the unit circle, right? Then the graph is rising, right? And it's keep rising. Right? And now I'm going to drag it out a little further, zoom it out a little further, so that you can see it's going to keep rising up. But it seems like there's a vertical asymptote at pi over 2, right? And then when you go forward up, it's going to make a jump, and jump on the other side. See what I'm saying now? That's why I was saying that there's a vertical asymptote at pi over 2 right here. Okay. And now I'm going to continue swinging it out. Right? The graph rising, and it stops rising and swinging back down like that. See the behavior like that? And then it seems like it's approaching another vertical asymptote at a 3 pi over 2, because here, as I keep completing my unit circle, you see how it swings to the other side like that? Right? So in the end, at the end of a 2 pi circle, at the end of a 2 pi complete period, and then we got one complete basic structure of our basic shape, right? Basic unit of our secant graph here. So yes, definitely, it looks like there are two vertical asymptotes here. One of them is at pi x equals pi over 2, and the other one is at 3 pi over 2. See what I'm saying now? So why is that? Why are there the vertical asymptotes? Because secant, remember, is defined as what? 1 over cosine of x, right? Remember that there? So think about a table of values. What happens when x equals pi over 2? And secant, we're taking the secant of x here. So what's the secant value for that? Fine. Maybe. That's why it has that vertical asymptote, and things just get broken up right around that vertical line. Right? And then the 3 pi over 2 also happens the same way right there. Okay? And you got a cosine of 3 pi over 2 is another 0, so 1 over 0, right? Give me undefined there. See what I mean? Okay, that's why we have, that's what explains for two vertical asymptotes again. So now I'm going to come back to that graph, put in the vertical line again. Go back on that graph, we have, right, a little bit, right? The vertical asymptotes happen at pi over 2, and then 3 pi over 2. We're all seeing it, right? So now, for secant here, it looks like there's a space, right? There's a center line still. See what I'm saying now? And now let me tell you the real truth here. Okay, if you're looking at the picture now more closely, right, and I can just disregard the asymptote, the actual complete secant graph looks like this. Right? See, it has all of that. So after we repeating infinitely many of those basic units, right, it forms into a shape like this. Okay, but see, now when I zoom it out far enough, you can see that no matter how far we go, there's always that empty space. There's always a center line here as well. Right? There's a center line, and then these parabolic shapes are here just swinging up and down, but away from that center line, away from that center line. Or in other words, we have an empty space. See, there's always an empty space right around that center line of our graph. You guys follow one? Okay, so. And then restricting that into one basic unit here. That's the structure of that. So let me reconstruct that picture of the secant here. Here's how I'm seeing it. So let's analytically break it down. So for this ordinary secant of x, right? See, you can go 0 to start. Center line is here right on the x-axis, but there's the generality is there's a center line. And then it starts, and right? It ends at 2 pi. And it starts at 0, according to what we saw in that graph. Right? And then there's a space. 1, -1, center line here. Halfway pi. Right? Are we good with that? And usually I would go with dotted line like this. Here's how I see about the secant. See again, at the quarters, right? First quarter we have vertical asymptote. That's the way how it is. You need to hold basic units. The vertical asymptote happens at the first quarter. You guys see that? No? Right. Vertical asymptote is happening at the third quarter. That's why on this ordinary version right here, the first quarter is a pi over 2. That's consistent with what we have observed earlier. And then the third quarter is a 3 pi over 2. How that peak goes. Halfway, we got a point right down here. Okay. See how I'm sketching it? Halfway, we got a point right down there. So just simply draw a cup pointing down, but peak at that halfway point, right? And then there's the lowest point is 1, drawing it up asymptotically. And then the 2 pi, comes to the end of the graph. Like this. That's how we draw that. See, there's always that space, that's between right around the center line. So you must understand that. That's for one specific cosecant. I mean, for one specific secant of x. But generally, the shape of secant looks like this. I don't even have to put the scales on any secant, right? Later on, you're going to apply all of the coefficients in, but the secant in general, center line is here, right? There's a space up, there's a space down, away from that center line. Okay? You know what I'm saying? No, but right on the center line, we have to identify where it starts, right? Where it ends. See what I'm saying now? And then the halfway point, right? The halfway point and the quarter point. Okay? I'm completely letting go of all of the scalings, all of the numerical labels. All I need is for the basic units of our secant. Okay? There's a space around that center line horizontally, and then there's a starting, there's an ending, right? At the first quarter, third quarter, there's a halfway point. And so the vertical asymptote always happens at the quarter point. The first quarter and third quarter. You guys following? Right. And then the graph goes like this. If it's the ordinary graph, right, then it goes, see, from starting point, right, but being away from that. So it's got to be outside of that empty space. Right? Remember, it's always going to have to be outside of that empty space. So I'll go up like that. See what I mean? Right. The halfway point gives me a point right down here. There's a cup pointing down inside of that distance between these two vertical asymptotes. But see, again, outside of that horizontal space. Right. And then this ending point right here. One basic unit. And as we keep repeating it, right, it's gonna replicate out and make the whole complete structure of that. That's how you catch it. That's how your secant looks. And then sometimes it may be sometimes due to a negative coefficient in front, right? It may flip upside down. Starting point, ending point, right? Halfway, quarters, right? There's an empty space around it. Right? Sometimes you may draw your graph like this. Vertical asymptote here, vertical asymptote there. Sometimes you may draw it like this. Right? That point always stays away from that empty space around the center point. This is the flipped version. And that point right here, going down. Right? That could be reflected through the center line sometimes. That's the picture of it. Keep that picture in your mind anytime it comes to secant. Right? You guys see that analytically right now? The start here, right? The end right here, right? Halfway. First quarter, third quarter. Okay. And then back at my time when I first learning it, I believe that was when I was right around you guys' age right now, these days. When I got into this, my professor was telling me, hey, look at that, does it look like a sack face again? Right? The frowny face, right? The two eyebrows again, the sack mouth again, right? So that's, at least I've been keeping that picture with me for those years when it comes to secant graph, right? And then we just sometimes when we need to, we just take the reflection of that through the center line. That's how we see that. And then we're gonna do now we're gonna break that down to the actual work right here. That those common information we can track down again. For this particular the ordinary secant here, we have a center line, right? We will have a center line at y equals 0, right on the x-axis. With any secant graph, we will have a center line. Okay? It has the amplitude here is actually replaced. I wouldn't say the amplitude is a non-applicable concept, but I would say the amplitude is replaced by, I allow me to introduce my own term here, the empty space here, right? Well, I'm saying up, right? The empty space right here is going to be 1. But 1 here, I'm talking about the center line empty space, 1 up and 1 down, right? So 1, I mean, empty space, 1 away from the center line. Each way right there, right? That's I call it the empty space. See what I mean? 1 space up, right, and 1 space down. That's what I meant. All right. And then there's the period. That's right. How far your horizontal window that's contained the one complete basic unit of your cosecant graph. So, of your secant graph. So we saw in the picture on the board earlier, it started at, see? The graph really start at it ended at 2 pi, started at 0, and there's that halfway point at pi right here, right? The quarter is pi over 2. The third quarter is 3 pi over 2, so you've got these vertical asymptotes, right? So, graph goes like that again. You see, you can do this just like me doing that all day without any error. Because once you capture that basic structure of the graph, it's going to make it a lot easier to draw. But now, your basic units for this ordinary secant of x starts at 0, right? Ending at 2 pi here. So that means what? The period here is p equals 2 pi. You guys drawing that information right there? Okay. And then yes, right here from the picture, we observe that the starting point, right? The starting point happened at x equals 0, right? And the ending point right here happens at x equals 2 pi. But again, constantly remind yourself the ending point is always in the start. And with that period window, how long that period window is.